And we're going. All right, so today's final is going to be the understanding of the TM30. All of this series, the 28th, and we're right on track, finishing up on time. And we'll be having some more trainings coming up. We just need to publish a list of those trainings and probably set out a little bit wider time period, maybe once every 2 weeks or once a month, depending upon how much information we have. Today's training is very simply, how do we see light? Give us a little bit understanding about what's involved there. And also understanding the differences between the current CRI and the color fidelity and color gambit that are going to be part of the new TM30 method. Then exactly what is a TM30? What does that mean, TM30? And what's that about? And then we'll go a little bit about how our LEDs measure up to this new standard. Muted. I do box open, so if you have any questions, feel free to put them in the chat box. I'll open it up for questions at the end. So, light, well, there's three factors that determine the perception of light. Notice it didn't say how we see it, it's how we perceive it. So one is the light source. Obviously, that has a big influence over how we view objects. The other one is the actual object reflectivity, how it bounces off of that object and how that object affects the light when it's being bounced off of it. And the third is the light detector itself, which is whether it be the human eye or some type of meter or measuring device. All those things have an influence over perceived light is. So if for example, if I change one of those, just change the light source to an all green, make it monochromatic, I'm going to have a very different view of that apple. You know, the rays are not going to show up. They're going to look either gray or dark brown, and it's going to look terrible. It's not going to look appealing to the eye. And so the light source itself has a direct effect. It's true if I change the apple or if I change the detector. Whatever there can actually make a difference. It's important to keep each one of these things are always referenced to some type of standard and through the details of those. So rendition. So basically, three elements of color rendition. One is fidelity. And so just as listening to an audio file, if you're listening to something over the telephone, it's a lower fidelity than if you're listening to it on a CD player or a vinyl record. So fidelity is basically the number of sounds you're able to transmit, and that can translate right over to light based on the number of colors that you actually have. The preference or preference is basically how they appear and are they pleasing or flattering. So there's a little bit of subjectivity to that, but you see, like in the apple example, the color directly affected whether it was pleasant to the eye or not, was what we were looking for. And then discrimination, basically it's the ability to see a difference between colors at the same time, so you get that transition and that difference. So we'll go to the next. So currently CRI is a color rendering index, and we basically index everything off some reference. So just an example, before we had a reference light. Typical thin filament is the reference light of choice and what most people use. And in this example, you can actually see an LED bulb, the actual spectrum of the LED with its peak in the blue and the yellow and red and green, compared to the spectrum of a tungsten filament is almost a linear line across the color spectrum. For our measurements, over in the bottom corner, you can see we actually have our color lamp that we actually use in our sphere here in the office measure up our LEDs and our modules. That one little lamp is a tungsten filament lamp, and it costs a little over $2,000, and actually traceable back to the National Bureau of Standards. So it's very, very important that everything's traceable and measurable, because if any one piece of the element is off, you're not going to get an accurate understanding of what you have. The current color rendering index is really kind of cool. They have a palette of 8 different colors. I have them highlighted here. 08, they're all pastels, and they shine a light from a known source, like that tungsten filament, and they get a reflectivity off of that particular light source. And based on that standard lamp, we can shine a from this lamp, the LED lamp, on the same colors, and then compare the reflectivity to the other one, so you can actually see the content of the different colors involved. And then each one of those is measured and averaged together, and then the average of those 8 color swatches incoming the CRI number. So when we say CRI of 70, that these color swatches average among all 8 of them will be 70 or above to the representative sample. Where the representative sample is considered 100%, RD would represent these colors at 70%, say 80 or 90 CRI. Now, not a lot of red in those samples. There are some in some of those colors, but it's a very important color in marketing and in groceries and things like that. So people are asking for an extra color, and that's where R9 comes from. So when people say, what's the R9 value of the LED, what they're saying is the next 6 are actually rendition colors that are available as well, and we actually use the number 9 because it is saturated red. These are considered saturated colors. We want to look at those and see what reflectivity of just the red is, so that we can, and that's where you would see an R9 of greater than 20 or an R9 of greater than 50. Different system for doing a color rendering index. But the problem with color rendering index is one does not take into account color saturation. So here's an example where I have a reference swatch, and the 2 test conditions give the exact same reflectivity. But you look at those 2 and actually see much bigger difference there in the color. And it has to do with the fact one of these is highly saturated and the other one is desaturated. So, but reflectivity is the same at those levels. So we're missing part of the equation of how these colors are perceived, and it has to do with our inability to actually modify the saturation level of the color. So here's the problems with CRI. One is that it disregards limitations of color samples in science that uses the older CIE chart, which is kind of dated today. Only 8 samples is actually used. It's only the pastels from the Munsell samples, and can actually selectively optimize. So what people can do is they can design their LED or their lamp source to match and give a good reading CRI index, but in real life it doesn't match what I would see. So they pass their numbers perfectly because they kind of work the LED to match up to the test, as opposed to creating a light that actually is useful. So what are some of the things it doesn't convey? Well, one of the things it doesn't convey is any colors. So, I say if I got this color, it's only the reflectivity. So if my actual color is shifting, I'm not seeing that. It decreases, increases in chroma, as well as information about specific hues, like skin tones and things like that. So they will be working trying to increase the human preference and there's ways they can do to kind of do that. Discrimination, potential is limited, and difference in color for any specific object can be very pronounced, as we showed in that other example. So, what do you do to make it better? Well, we have the fidelity, preference, and discrimination. Well, preference and discrimination both kind of tie into the degree of saturation. But they're pretty easy to improve. We just increase the number of colors. So as we increase the number of audio bits, we can increase the number of colors that we actually do measure and improve that score. So that's easy to do. And then as far as the saturation, we got to come up with something new to kind of saturation in a better way, or to express that saturation. TM30 is set to do. It's trying to improve on the CRI and come up with better measurable things. So what does TM30 mean? Well, it's Technical Memorandum number 30, and it's published by IES, and it's for evaluating a light source color rendition. And I'm not going to go through this whole thing, but it basically creates two new measures of color. One, color fidelity, named R, and the other, color gambit. And gambit has more to do with actual location of the color, if it's shifting, and the saturation level of the color. These documents are available at the online from the IES bookstore. It's a $50 price. You can go link right there where you can click on and go actually download it and enjoy yourself with all the math. But I'm not going to go into the math today, but it's they want to look at it. So what to do? So first do is they're going to increase the number of samples from 8 to 99. And here comes the difference. And it's they added a lot more in the reds and browns to the actual color samples. So what they're trying to do is capture more of those skin tones and reds that people are looking for in this sample. And the human perception, these colors were selected particularly to try to hone in on the human perception. Some thought into which colors they actually were going to put in this sample set. So before we took the 8 different reflectivities and averaged them, they now take 99 reflectivities and average that. And here's the map to kind of show you how to do it. Simple, there's a scaling factor and an average. It's not hard. And then add a low-end limit. So there's a logarithmic function there for the low-end limit. Because the color CR numbers could actually be negative in the old, and they wanted a scale from 0 to 100. So that's how they did it this way. That's quality. Pretty simple, pretty straightforward. We're just increasing the number of colors. Narration, how do we represent that? Part of the problem is we use the CIE XY chromaticity diagram, and this has been around since the 70s actually. Some dates even that, been upgraded since. But really it's a 2D representation. It's an XY representation of the color. And can't really represent saturation. That's a third dimension that we have to kind of have. So how do we get from this to something else? Well, the Munsell diagrams, that's the next one here, and you can see these are three-dimensional. And so what it is you have the color hue around the circle, and then as you approach higher and higher and closer towards the center, you get less desaturation, and as you approach further out and out near the bottom, you get more saturation of those colors. So we get this one and kind of use it in a flat format, and I'll show you that in the next slide. So here's a square representation of that color Munsell pattern, if you want to think of it like that. And so what you can do is going around the perimeter changes the actual hue or color. And then we have a reference color, and we know where that should be, right in the middle. And if the color shifted due to hue change, it will move around clockwise or counterclockwise in a type of direction. This is actually moving towards the yellow. And if it's actually becoming saturated, it will move outward from the center. and it's becoming desaturated or white light. It becomes towards the center. So you can see the shifting of the color versus the reference color. So we take 9 points and we plot them on this chart. And notice that they've sliced this chart into 16 different wedges. And so these wedges has a certain number of colors in it that came out of that color chart and the apple pattern. And then they average those points, those colors together. And over here on the right, you can kind of see where the gray dot is where the reference is. The reference source, that would be your tungsten source. And then the source would be your LED source or lamps, testing lamp. And you kind of see the actual location, how it moved from where the reference should be to where the actual color was measured. So those, and I look at just the differences. So like here in sector 1, I have shift kind of over, it gets saturated, and then color shifts a little bit clockwise. You can see how that moves here. Well, it didn't move. If my red dot was right on top of my gray dot, then it would stay right in this same spot. This circle that's over here in the vector graphic diagram is to represent how the colors are shifting from the reference. So I draw that. You kind of see I don't get a quite perfect circle. I get kind of a weird egg shape. And you can see where the sides that I have saturation, and then areas where it goes outside the circle is increase in saturation. And there's also rotational direction in there so that I can see that with some of the other diagrams. Kind of where we're starting to head. So then we take all those numbers, all 16 of those numbers, and we average them. So average called it index, which is basically all of the tests, all of the reference, and the indication on approximately how close in saturation you are from one sample to the other, as well as color shift as well. So we now have color fidelity, RF, and we have color gambit, which is RG. And so they draw that on a chart here. And this chart has obviously RF along the x-axis and RG along the y-axis. Reference point, this is your tungsten point right here, so that's right at 100 and 100, so that's perfect. So if I have more saturation, then my test subject will go under 100 on the gambit. If more saturation than the reference, I would go above 100%. Then my fidelity would move from the right side towards the left. So here's an example of different spec outputs and all being 3500 Kelvin with an RF of 65 and an RG of 115. You would be able to see exactly where that resides and how much. And the closer I am towards the point of this cone, the better I am as far as being to that true tungsten reference. The software to do all this. And this output of that software would look like, so here color distortion, that's the rotation of the actual color hue, and then here's the actual vector graphic that we went through, along with the traditional spectral output that we're used to seeing. And this is the actual chromicity chart where we actually have our subject, and then all these other dots were other references that we could compare them to. So we have tungsten here, and this is where we ended up with this particular test subject. So there we get a fight out of the sphere that's right into the spreadsheet, and it does all these calculations. So it's pretty simple to do. It's a matter of doing it. So how up on these items? So actually measure up pretty well. You got in mind that the LEDs from Samsung are actually have their genesis out of the TV world. So our phosphors and our color mixing has pretty good color across the spectrum. And we don't have as many spikes as a lot of our competitors may have. So when we get like our 90 CRI product, well, you can look at this one of 3,000 or 3,500 Kelvin 90 CRI. You see it's shifted, but we have like a 90, almost a 93 R9 on that. Very close to a perfect circle in a lot of these 90 CRI products. You can on the 80 CRI, everything's kind of shifted, a little bit distorted, but for the most part, we're either undersaturated or right at the proper saturation point, sometimes a little over, and we average out. So like our saturation here on 5,000 Kelvin is almost 100%, but some of the colors were unsaturated, but some of the colors were oversaturated, so we end up with a nice average there. So I think moving forward, we're going to be adding this type of data to our sheets. It's taking this in. Not too many people have actually spec'd what they want the color gambit or color fidelity to be based on TM30. We will have data available, and we can generate that data on customers on an as-need basis. But I just want you guys kind of an idea of what this is, and it's coming. It's not actual considered standard yet. It is published, and they are requesting people to start using it. So be if somebody says, hey, I need TM30 information, you can Samsung, and it's readily available. That's all I had on this today. I'm going to stop the recording now.